Alright guys, this is pre-calculus 4.1.3, and this is the kind of last section of us talking about these factored polynomials and looking at their graphs. We're going to take a look at these 9 graphs first. So these you're going to see on A, D, and G, so kind of going vertically here, we have the exact same graph, it's just being shifted. So we're going to be looking for distinct real roots. So there's two kind of key qualifier words in there. The first one being distinct, the second one being real. So distinct means that they're all different. Why that's important is a double root, which is where we have things that are kind of touching. Right. So this one here, this is when we have the same factor twice. So it's like x minus 2 to the d second power, that kind of thing. So you get 2 and 2 as your answer. So you get these same answer twice. So those would not be distinct, right, because they are the same. So, and then real means that it's not a imaginary, so it's going to appear on our number line, which is also our x-axis here. So the first one here, we have 1, 2, 3, 4 distinct real roots. Down here on D, we have 1, 2, 3. So there's 4 real roots, but only 3 distinct roots, because this one has that double root there. And then G only has 1 distinct real root, because it is because you have this double root here, and that's the only place where it touches our x-axis. So looking at B and our kind of middle ones here, we have 2, here we have 1, here we have none, here we have 3, here we have 2, and here we have 1. So the question becomes, well, how many can I have, right? So that's what we're going to start to explore here in a little bit. So we're really going to start to work on number 36, but I'm just going to hop back over here and we'll just talk A about that. So on A, we could have 4, right? We could have 3, we could have 1. Could we have 2? Yeah, right. If I move this graph down just a little bit, we'd have 2 distinct real roots. And we could also have none, right? We could move it up even further, and it never touches the x-axis at all, right? B, or this like middle grouping, we're really seeing all 3 of the possibilities. Either we have 2, either we have 1, or we have none, right? And then on C, well, here we have 3, here we have 2, here we have 1. Is it possible for us to have no distinct real roots here? And the answer is no, because if you think about it, this graph will go up forever and down forever, so there's no place you could ever shift it where it would not be crossing the x-axis at least once. Whereas the left and the middle graphs, those you can have no distinct real roots for, by just having them be above the x-axis by enough. And the difference there is that our first and our middle ones are even, right? So those are going to be even graphs. Sorry, graphs of even degree polynomials for us. And then that far right one, that is odd. So it's an odd degree, so we can't have it ever have 0. And we'll talk more about kind of why that is here in a second. All right, so let me hop back over to this. Okay, covered those. Yes, so the numbers which we can have. So this graph here on our left side, this is a 4th degree polynomial, and the largest number of distinct real roots we could get was 4, right? B was a 2nd degree polynomial, and the largest number of distinct real roots we could get there was 2. This one was a 3rd degree polynomial, and the largest number of distinct real roots we could get is 3. And that's not by coincidence, right? That's always going to be the case. The degree distinctly tells you the number of roots you're going to get for that particular graph. So that brings us here to what's called the factor theorem, and then the rational zeros theorem. So the factor theorem says, well, if I have a value that is a root, right, and I plug that into an equation, I'm going to get 0 out of it as my solution, which is again why we have those polynomials being equal to 0 when we're trying to solve them, because it's what value of x makes it 0, and those are going to be your roots. Okay, and that seems kind of, well, duh, I've been doing that for quite some time, what do I care? And it's because that's how we're going to be able to factor polynomials that are above the second degree. We've been factoring stuff that is x to the second for quite some time, but if there's ever x to the third, x to the fourth, stuff like that, we either need to just do a greatest common factor on it, or we do like a difference of two perfect squares, some other of those kind of very specialized factoring techniques, which don't always work, but the ones we give you as math teachers do. Right? So we're going to try and figure out, well, how can we factor anything, even these larger and larger powers? And that's going to be fairly important, even though it might not seem so right now. And then the rational zeros theorem, what this is that it's basically our way of finding the possible real factors of or real roots of a particular polynomial. And here's kind of how it works, right? So it's going to seem weird, but we're going to only look at the leading term and the final constant. So here, 2 and 6. Now I'm going to list out every single factor of 6, and I'm going to put that on the top of a fraction. And every single factor of 2, and put that on the bottom of the same fraction. So all my factors of 6 are 6 and 1 and 3 and 2, right? Just those 4 values. All my factors of 2 are just 1 and 2. So on the top, I would have 1, 2, 3, and 6, which is what they're showing here. Now, and on the bottom, I'd have 1 or 2. Okay. So what I need to do now is find every single possible combination of the top values and the bottom values. So I could have 1 over 1, or 1 over 2, or 2 over 1, or 2 over 2, or 3 over 1, or 3 over 2, or 6 over 1, or 6 over 2, right? And if I take all of those and I eliminate ones that are the same, like 1 over 1 and 2 over 2 are the same, right? So I really don't need those, so I can just kind of take those off. I'm left with just these. So I got 1, a half, 2, 3, 3 halves, and 6. But I also need the positive or negative options there. So I'm going to put a plus or a minus in front of all of those. So we get this decently long list of numbers, right? 1, 2, 3, 4, 5, 6, but then they're plus or minus. So really, I have 12 possible numbers here. So out of those 12 possible, those are the only possible numbers that I could get a real root from in this polynomial, right? That doesn't mean that it's guaranteed to be there, or that all of them are there, but if I have a real root, it has to be one of those. And since this is a third degree polynomial, we know it has to have at least one real root, so at least one of those 12 is going to work. And this is the downside. It's one of those 12 options, and we just have to guess and check those 12 until we find the right one. Benefit is guessing and checking 12 is better than guessing and checking out of every number that has ever existed, right? So that is where this factor theorem we talked about earlier comes into play, right? We take those, we plug them in, and we see which one gives us 0. The one or ones which give us 0 are going to be our real roots. And that's effectively how we're going to be able to find those and then eventually help us factor. Okay, so let's try that out. This one we're doing that. Yeah, okay. So I'm going to grab a piece of paper. I didn't have one ready, and that's my bad, but it won't take me very long. It's ready right now. So I'm going to kind of not really follow the problem that is in front of you right now. I'm just going to kind of work through it and kind of show you I do it a slightly different way, so I just want to kind of show you guys that. So it's not going to be as structured, kind of following step by step there. But so we are looking at x to the third plus 2x squared plus 2x minus 5. Okay, so that is our polynomial we're trying to factor here. Okay, or find all of the roots for it. So I'm going to do what we just talked a about and say, well, my factors of 5 are 5 and 1. That's it. That's not too bad. My factors of 1, because there's like that invisible 1 there, right, are just 1. So I could have 5 over 1. I could have 1 over 1. Right? And I could have plus or minus on each of those. So really I only have 4 options. Plus or minus 5, plus or minus 1. Okay? So I need to check and see which of these work here and give me 0. So I'm going to grab my calculator and start plugging things in. Right? So if I do, let's try 5 first. Well, 5 to the third plus 2 times 5 squared is 25, plus 2 times 5 is 10, minus 5. Oops, I must have typed something in wrong there. Oh, I had the answer should be plus. There we go, just delete that. Oh, it was 2 times 5, so it's 2 times 25, so 50. Okay, let's just do that. There. Right, 180. No, that is not 0, not even close to being 0. Okay, well, how about if I plug in a negative 5? Well, that's going to be negative 5 to the third plus, that would still be 25, so plus 50, minus 10, and then minus 5. Well, I'm still not anywhere near 0. Don't got to worry about either of those ones working. Well, how about a positive 1? If I plug in 1, well, that's going to be 1 plus 2 minus 5. Hey, that's 0. So positive 1 works. Let's test out a negative 1. So that'd be negative 1 plus 2 minus 5. That one doesn't work either. So the only one of those which worked was a positive 1, which tells me that positive 1 is a root of this particular polynomial. So the next question is, well, what factor would give me positive 1 as a solution? Well, that's the factor x minus 1, right? Because this would give me that as a solution to it. So I know that this is a factor of this. So what I want to do now is divide it out. So that's that kind of box method strategy we talked about in the past. So I'll divide out the x minus 1 from x to the third plus 2x squared plus 2x minus 5. So going through that process one more time, I'm going to put my x to the third here. Say, well, what times x is x to the third? Well, that's this x to the second. X squared times negative 1 is going to be negative x to the second. What plus negative x to the second gives me 2x to the second? Well, that's going to be 3x squared. Well, what times x is 3x squared? Just 3x. 3x times negative 1 is negative 3x. What plus negative 3x is a positive 2x, and that's going to be 5x. So then what times x is 5x? Just 5. 5 times negative 1 is negative 5. I have a remainder of 0. And you should always have a remainder of 0 here, because we said this is a factor, so this should, that this is a root, so this should be a perfect factor, right? So what I've just factored this into, I factored this original into this times this. So it's now x minus 1 times x squared plus 3x plus 5. There, I'm factored. Okay. And now I can say, well, do I want to factor this part? And only, yeah, you would want to factor that too. But I know it cannot factor, even prior to even looking at it, because I have already checked all 4 of the possible real roots, and only one of those 4 worked. So even though there should be 3 answers because of this 3 here, only one of them is real, the other 2 have to be imaginaries. And I'm only going to get those imaginaries by doing the quadratic formula on whatever's left here. So if I wanted to do that, that is x is equal to negative b, which is negative 3, plus or minus big square root of b squared, so 9, minus 4 times a, which is 1, times c, which is 5, all over 2a, which is just going to be 2. So that is going to be negative 3 plus or minus 9 minus 20 is going to be square root of negative 11 over 2. And that's not really going to look any better than that. I can write it with an I. I'll just have negative 3 plus or minus square root of 11i. I'll put the I in front. Over 2. So there's my 2 imaginary solutions, and my real solution there was the positive one. Okay, so that's the process. Right now, we're really not going to focus as much on this portion here, but that's effectively what we're doing. All right, so let's hop back over here and take a look at this. So for the sake of time, I'm not going to have you do all 4 of these, A, B, C, and like D. Pick 2, try those out, see what you get, and then I'll throw up the answer key and you can check those out. All right, so what you should get for those answers there, there's answers for A, B, C, and D, right? Again, that's just kind of following that same process we just went through. Let's hop back over here. And I want to talk about 39 real briefly. So on 39, we're trying to talk about what kind of answers would we know that we get. And what you likely noticed on those last ones was solution-wise, whenever we had an imaginary, they always came in these pairs. So this was plus or minus 2i, plus or 1 plus or minus 4i. The one that I had earlier, if we change back over to this view, was 3 plus or minus I rad 11. So it's always had that plus or minus in front of the I. So if we hop back over here and talk about why that is, if we look back at these, okay, so on my, here's a third one, a third D3 here, right? I have 1, 2, 3 reals, 1, 2, 3, because this is a double reel. And I have 1 reel, and then that's it. So those other 2 have to be a imaginary. So what you'll find is it's impossible to make it so that you have only 1 imaginary root. So if I have a 4th degree polynomial, it's impossible for me to have 3 real roots. I can have 3 distinct real roots, but not 3 real roots total. So like on part D here, right, these are 3 distinct, 1, 2, 3, but this one here is a double, so that's really 1, 2, 3, 4 real roots total. Right? And if I go down to G, now I have 2 reals here because of this double. Then my remaining 2 have to be a imaginary. So that's another pair of imaginaries. And what you'll find is no matter what you try and do, you will always get imaginaries in pairs. Right? It's impossible for you to have an imaginary number by itself as a root. Okay, so if we hop back over to these, what you also notice about those pairs is that they're always what's called a conjugate pair. Right? The conjugate is it's the same thing, but one's positive and one's negative in that kind of middle term. There's more to being a conjugate than just that, but a conjugate will always multiply and have a lot of the kind of ugly parts cancel out. So what you'll find is with these conjugate pairs of imaginaries, if you multiply these 2 things together, there's no more i's. And that's kind of what makes them special for us. Right. Also, they always come in these pairs. So I have -3 plus I and -3 minus I. That is fine. That could be all of the roots that I could ever have. Right. Same thing down here on B. I have 5 plus rad 3 and 5 minus rad 3. So even when they weren't imaginary, they still came in those pairs for us when we tried to kind of solve them out. C, we have -2 and and rad of 7. Those work just fine. We don't have to have more. But then we get to part D, right? So on D, I have 4, and then I have -3 plus I. Me being told that, I know there has to be at least a third degree polynomial here, and there has to be at least one root that I'm not seeing. Now, how do I know that? Well, I only see one imaginary number there. I see -3 plus I, and those have to come in conjugate pairs. So what's the conjugate pair of -3 plus I? Well, -3 minus I. So that would be the third root that has to go with those two. That's what they're kind of trying to get you to kind of start to notice here. All right. So with that, we've already kind of talked about this real briefly, but the number of real and non-real roots. Let's just do C really quickly. So there's 3 real roots here because this is a double, and then here 1 real, 2 imaginaries because I'm missing those. Here there's just 2 imaginaries. Here 2 real, 2 imaginaries. All right. With that, here is our homework for 413. We are doing 42 through 49, and I will talk to you guys next time.